All right, so today we are going to go over decomposition reactions, which is the reverse of a synthesis. So synthesis, if you recall, is going to be A plus B, and this will give us AB. So we're putting an element with another element and making a compound. So this is where we crisscross our charges. Okay, so for example, if we have, let's just say Na plus S, okay, well, if we want to put these two together, they're going to transfer electrons. So we would have Na is plus 1, sulfur is minus 2, so we would create Na2S, and then we would just balance this. Decomposition is going to be the opposite. So now we're going to have one reactant, and we're going to break that apart into smaller pieces. The only thing you need to pay attention here are your Hunkelbriefs or your diatomics. Okay, otherwise there's no subscript. So we're not paying attention to charges at all because charges only matter on when we're putting things together, but we're breaking them apart. So we're putting them back to their normal states, so their individual states. So for example here we have carbon and sulfur. So we have a compound. So this is our compound, which means that we have to break it into each of their corresponding elements. So in this compound we have carbon, we have sulfur. So we are just going to break it into carbon and sulfur. We need to check for diatomic. So if it's not a diatomic, it's going to stay as a 1. If it is a diatomic, it's going to get a subscript of a 2. So for example, hydrogen's diatomic, so it would be H2. Here, carbon, not one of our diatomics, so we leave it as a subscript of 1. Sulfur, not one of our diatomics, so we leave it as a subscript of 1. This 2 does not transfer. That 2 is there because of how it's sharing electrons in the compound. So when we break it apart, it goes back to its natural conditions. So then we would just balance this. Okay, so we would add so we have 1 carbon, 2 sulfurs. We want to put 2 sulfurs there. The last thing that we can do here is we can add our states of matter. So if you remember, black elements on the periodic table are going to be your solids. Blue are your liquids. And then your red are gases. So carbon we look, carbon is a solid. Sulfur we look, and sulfur is black, so it's also a solid. And that is our balanced reaction. So we'll try 2 more together, and then I'll have you guys try the magnesium oxide on your own. So we have AlCl3. So we're going to take Al plus Cl2. Okay, so we broke it. We have Al by itself. We're breaking these apart. This one gets no subscript because if we look here, there is no aluminum in our Hunkelbrief. So that is by itself. Chlorine, I gave a 2 because if we look, chlorine is one of our diatomics, so it becomes Cl2. So when it's by itself here, so it has to be by itself in order to pay attention to diatomics. Okay, it's by itself and it's a diatomic, so we put a 2. Now we're going to balance it. A key to remember when you're balancing is to always make your odds even. So here we look, we have an odd chlorine. So we have 1 Al, we have 3 chlorines. This side we have 1 Al and we have 2 chlorines. Okay, well 2 and 3 can never go into the same number. So we are going to make our odd even. So we will put a 2 in front of there. That changes chlorine to 6 and also changes aluminum to 2. Now we're going to go on this side. Well, let's fix our chlorine. We have 6 and 2, so I can put a 3 there. That gets that to be a 6. The only thing that balances the aluminum, so I'm going to put a 2 there, and that's where we get our final reaction. Okay, the next one we're going to do together is the iron 2 oxide. So this one's a little tricky because it doesn't give us our reactant. We have to figure out what our reactant is here. So I am going to write our reactant out. So we know it's a compound. So we know that electrons are being transferred. So we have to figure out, well, how are they being transferred? In what ratio? So we know that iron is Fe. And remember, that 2 tells us that it has a +2 charge. Oxide is just oxygen. Well, oxygen we know has a -2. Okay, you should notice +2, -2. Those would cancel out. So iron 2 oxide is FeO. Okay, so we only have one reactant, so this compound is AB. So we're going to break it into its parts. So its 2 parts are iron and it's oxygen. So if it's by itself, the only thing we have to check for, again, we don't care about charges. Charges are when we're putting things together. We're breaking these apart. So the only thing we have to pay attention to are if it's a diatomic. So can it exist by itself or does it have to come in a pair? So I find iron, go up here. Iron is not one of my diatomics. So I leave it as 1. So iron can exist by itself. So it's going to be by itself. Oxygen, I look, oh, okay, look up here. Oxygen is a diatomic. That means oxygen cannot exist by itself. And since it's not in a compound, it has to be with another oxygen. So now we have our reaction, and all we have to do is balance it. So we're going to add our coefficients. So we have 1 iron and 1 oxygen. We have 1 iron, and we have 2 oxygens. So we're going to put a 2 there. Okay, well that changes this to 2. So it changes our oxygen to match, but it also changes our iron. So now we're going to go over here and we're going to put a 2 in front of the iron. So now everything is balanced. So I want you guys to try to do MgO on your own and answer the question at the end of the video. Okay? And then when you guys are finished, if you could work on day 2, that'll go over different types of decomposition reactions.